So what we're going to do is look at chapter 4, the review problem number 9. It says find the indicated probabilities using the geometric distribution, the Poisson distribution, or the binomial distribution. Then determine if the events are unusual. If convenient, use the appropriate table or technology to find the probabilities. The mean number of heart transplants performed per day in a country is about 5. Find the probability that the number of heart transplants performed on any given day is exactly 6, at least 7, and no more than 4. So if we analyze this question, notice it gives us a mean number of heart transplants, which is 5, on a day. And so this meets the criteria for a Poisson distribution because we have an average number of events that happen over a given interval. So we're going to use the Poisson distribution to find these probabilities. And so let's move our stuff over. Now remember that an unusual event has a probability less than 0.05. So our mean number of heart transplants is 5. And what we want to find is the probability that on a given day we have exactly 6, that we have the at least 7, which means we have to be greater than or equal to 7, and no more than 4, which means that we have to be less than or equal to 4. Right, so we'll put these in probability notation. So having a Poisson distribution, what I'm going to do here is on page A12 in Appendix B is our Poisson distribution for a mean of 5. So I'm going to write down what the probabilities are. And since our highest number is 7, I'm only going to write the probabilities up to 7. So the probability of 0 is equal to 0.0067. The probability of 1 is equal to 0.0337. The probability of 2 is equal to 0.0842. And the probability of 3 is equal to 0.1402. The probability of 4 is equal to 0.1755. The probability of 5 is equal to 0.1755. The probability of 6 is equal to 0.1462. And the probability of 7, which is the highest one I'm going to put in here, is equal to 0.1044. So for question A, it says, hey, what's the probability that on a given day we have exactly 6 heart transplants? So I come over and I get 0.1462. So the book asks for 3 decimal places. So we'll put 0.146. And our table finds us the answer quite quickly here. For part B, we want to know for the probability of everything greater than 7. That's up to a billion, trillion. It's infinite. It goes on. And so we have these infinite probabilities that keep piling up over top of our probability. But we can think of the probability of everything greater than 7. Well, it has a complement. It's everything that's less than 7. It's complement, right? Because if I add up all the probabilities of everything greater than 7 all the way up to infinity, well, it's still, that probability still has to add up to 100% with everything less than 7. When everything less than 7 is on my table here. So I can have 1 minus 0.0067 plus 0.0337 plus 0.0842 plus 0.1402 plus, let's see, 0.1755 plus 0.1755 plus 0.1462. Notice I don't include 7 because the complement is everything less than 7 non-inclusive. And so I run across and make sure I get everything onto my calculator perfectly fine here. Put the parentheses in so the negative sign works out for me. And I get, let's get a move up over, oops, 1.4, nope, where did it go? I get, sorry, clear, 0.2378. 0.2378. Again, the book wants 3 decimal places, so 0.238 is our probability, or about a 23% chance, 23.8, right, if we talk in percentages. And then for C, we want the probability of everything less than or equal to 4. So I'm going to just highlight, I'm going to add these probabilities, because that's everything less than or equal to 4. So I'll add those probabilities up, P of x less than or equal to 4, and I'll just say, hey, it's the sum of P x equals I. All right, and we're going to go from 0 to 4. We're going to sum everything up to 4, so we add all of these probabilities up. 0.0067 plus 0.337, I need to get my 0 in there, 0.0337 plus 0.0842, so 0, 1, and 2 plus 0.1402 plus 0.1755. And what I get is 0.4403, rounding to 3 decimal places, 0.440. And so here we used our Poisson distribution table to get our values for us quickly, and we used our complement to solve for when we have greater than a value, and we summed up everything for a particular, again using our probability rules to add our probabilities.